everyone. So this video is going to go over put tablet mode on. So this is going to go over the specific heat and heat capacity notes, what we did in class, and kind of just the conceptual pieces behind specific heat and heat capacity. So we need to remember the definition for heat. We define that a few times in class, and it's really, really important that you remember it. It's the measurement of transfer of energy. It's not just, how the temperature of something, it's the movement of energy from one system to another. And what we did in class is we took the time to kind of explain what system means. And basically, we said that there is no one thing that it means. It's whatever you decide it to be. So if we picture the lab, we had like a hot plate. We had, hang on, my phone's ringing. Okay, so we had a hot plate. We had a beaker on it. Oh, that's a real nice beaker. Oh, yeah. And then we had, a thermometer thing in there. There we go. Look at that. Beautiful. So we had our setup here, and we called the system the beaker, or the water inside of it, right? The ice, the water, the stuff inside of it. And we called that the system because we were putting energy into it. And then we were looking at what happened as a result. Now, we could have said the system was the hot plate, but that wouldn't have really made sense because it's irrelevant. It doesn't really matter. But when it matters, it's because defining whether the system is endothermic or exothermic, when defining that, it depends on what you say the system is. I feel like I didn't make very much sense right there, but I'll explain it a little more clear. Okay, so when something is endothermic, heat flows into the system. So if we said that the system was, again, our beaker, I'll try to draw it a little better this time. How about that? So our system is the beaker, and we have it on a hot plate. Everything that's not the system is considered the surroundings. So here in this case, if we have an endothermic exchange, heat is flowing into the system. And if this is our system, then it would be endothermic because heat is flowing from the surroundings, aka the hot plate, into the system. And I'll get to what this means here in just a second. But we could also look at an exothermic exchange. Say, for example, we have some wood. Here, let's draw. This is my campfire, and it's burning. There's fire. Fire, yay. So here in this case, the wood is the system, and heat is flowing out of it into the surroundings. So it's leaving the systems out. It's given off, so it's exothermic. Now, when we talk about that, we always say that the surroundings are usually us. It's how we would feel. So if here we are at our campfire, are standing in front of a fire, how does it feel? It feels hot. And it feels hot. Oh, I can't circle it in black. It feels hot because the system is, expending heat. It's giving energy to us, and so it feels hot. An example where we are the surroundings for an endothermic exchange would be, that's a hand, big hand. I don't know. Don't worry about that. And here I have an ice cube. If the ice cube is the system, system, ice cube, well, then it's a endothermic heat exchange because my hand feels cold. It feels cold because it's literally taking the energy from my hand. The energy in my hand is going into the ice cube, and so it feels cold. So we have endothermic, exothermic, and endothermic, exothermic represents the direction of the flow of heat, whether it's into or out of the system. And that has to do, when we get to energy and whatnot with the calculations. So endothermic, exothermic. The next thing we talked about then was heat capacity. So think of heat capacity. If you break down the word heat capacity is like how much stuff something can hold, its limit. And heat capacity is how much heat something can hold, how much energy it can pull in until the temperature increases by 1 degree Celsius. So say we have down here a 250 gram steel cylinder. So at the top here, and then at the bottom, we have a 50 gram steel cylinder. Now the heat capacity is how much energy it takes to increase the temperature. So do you think that the larger cylinder would have a greater heat capacity or the smaller cylinder? Think about it. Hopefully you answered the larger cylinder. Let me see if I can get, oh, hang on. Yay, you were right. So, oh gosh, this is gonna take forever. Okay. So the 250 gram steel cylinder has a larger heat capacity because it takes more energy, so it requires more energy to increase the temperature by 1 degree. If I put the same, so let's say we are out in the sun, here's the sun's giving energy to both of these things. After like 1 minute, this is gonna be a lower temperature than this guy because it's smaller. There's not as much stuff, not as much matter to heat up. Okay, so that one's usually pretty obvious for students. However, this one is a little bit more complicated. So here now I have an iron block and a wooden block, and I want to know which one has the greater heat capacity. Take a second and think about it. So normally students always want to say the iron block has the greater heat capacity because it gets hotter faster. But remember, the heat capacity is the energy that it stores, that it holds on to, and then increases the temperature. So picture it like this. If I'm out, or I have a stove, okay, so here's my stove and I have my burners. It's not a fire stove, it's an electric stove. And then I have a wooden spoon, here's my spoon, that I set on the hot burner. And then I have a metal spoon, for some reason it's pink. My metal spoon is on the same burner. Now, I walk away from the thing, and in a minute, I come back. Which one, if I touch, is probably going to hurt? The metal one. The metal one is going to be hotter. Why? Because it's taking in energy, and it's increasing in temperature. It's easier to increase the temperature. Whereas the wooden block, it's receiving the same amount of energy, but it's absorbing, it's holding onto it, and it's not increasing in temperature just yet, or it's increasing in temperature at a slower rate. So it has a greater capacity. It holds onto that energy. It can hold on to more energy before that temperature increases. So we should say that the wooden block has the greater heat capacity, again, because more energy can be put in before that temperature increases. Now, we're not usually going to have like arbitrary amounts of random substances. So scientists wanted to kind of take this concept of heat capacity and make it quantitative. And to do that, they came up with specific heat capacity. They're real clever. The specific heat capacity says that specifically 1 gram of a substance, if I wanted to heat it up by 1 degree, this is the quantity of energy, this is the amount of energy that it would take to do so. And therefore, specific heat capacity is dependent upon composition only. It just matters what it's made of. Because, say, if I go back here, if I'm looking at this steel cylinder versus this steel cylinder, well, if I take a gram out of here and a gram out of here, I have a gram of steel no matter what. So they're going to have the same specific heat. However, if I took a gram of the iron, a gram of the wood, well, that would be different. It would, be the same kind of as our first example. So specific heat capacity is just a quantity, a number that says specifically how much energy it would take to raise the temperature of 1 gram of a substance by 1 degree Celsius. And here on this next slide, I'm just going to show you a list. And here are just some specific heat capacities. Random objects have a set value for their specific heat. And you can Google this. You can say, what is the specific heat of liquid water? What is the specific heat of solid water? And Google will tell you. And so you can ask different questions from this, like if you had all of these out in the sun, which one would be the highest temperature after a certain amount of time? And it would be the silver because it has the smallest heat capacity. Therefore, it's going to absorb that energy and it's going to increase in temperature faster. So in a nutshell, that is specific heat and heat capacity.